A2 Maths, Integration by Substitution. Right, so what I'd like you to do is just have a go at integrating this function using just your laws of indices and your skills from the previous lesson. Okay, so pause there, have a go at it, and see if you get the same answer as what I get. Okay, so if we're looking at using the laws of indices, what we're looking at is the fact that you're adding the powers there. So we know that if we add the powers, we can split this up into e to the ax times by e to the bx, where a and b are just some constants and we're integrating in terms of x. Right, so because they're just constants, that e to the b part can be brought outside the integration, because if b is a constant, then the exponential of b will be a constant. So e to the power b will be a constant. So therefore, I'm just dealing with integrating e to the ax. Now from previous lesson, we know that if we integrate e to the ax, that means that we have e to the ax divided by a, or 1 over a e to the ax. Okay. Now I can neaten this up slightly. So I've pulled, what I've done there is just pulled the 1 over a to the very front. I've put the e to the b back next to that. And the reason for that is now what I can do is I can use my laws of indices again and put these back together to end up with this answer. So if I'm integrating e to the ax plus b, then the answer is just going to be 1 over a e to the ax plus b. And you'll probably notice that the differentiation of ax plus b is a, and that's why you're dividing by there. So this works out quite nicely. What we're going to look at is proving that result using something called integration by substitution. Right, so if you just grab your notebooks out then, title is integration by substitution, and let's look how we use integration by substitution to integrate this function. So we need to notice that it is a composite function. In a very similar way that you would, if you were differentiating this, you'd think about using chain rule because we have a function inside a function. The same reasoning for that, you would use integration by substitution. If you have a function within a function, then you look at doing some sort of integration by substitution. Now the inside function in this case is the ax plus b. So what I'm going to do is I'm going to allow the substitution u to equal just ax plus b. Now the problem is if I wrote down the integration of, let me just show you what I mean. If I wrote down the integration of e to the u dx, so I substitute it straight in, the problem with that is that you're integrating this function, this first function, e to the u, with the variable u, in terms of x. And because these two things are different, there's a u value there as a variable, there's the x value at the end that I'm integrating. Because these two are different, I can't just do it. I can't just write that as e to the u. They have to be the same function there, the same variable. Okay, so how could I get this dx to be du? And the answer, because there's the issue, the answer is I'm going to have to differentiate. So I'm going to differentiate u equals ax plus b to find du over dx. Now if I do that, as you can tell, if I differentiate this part, I'm going to end up with just a. And because I end up with just a, I can now rearrange this equation. I can rearrange this differentiation equation. I can take the dx to that side, and I can then divide by a. So just make sure you're happy where this comes from. I've taken the dx over that side and got du equals a dx, and then I've divided by a to get dx on its own equals 1 over a du. Now this is why it's called integration by substitution. You don't just substitute that part into there, but you also do some sort of substitution for the dx bit as well. So I'm going to substitute this dx in here, now I've figured out what it is, into there. So I end up with 1 over a, which is from there, e to the u, because I substituted u for the ax plus b, du, because I know that the dx was 1 over a, which is that bit, du. And now I'm in a position to do a very easy integration here. I can now look at this and say, well, e to the u du, if I integrate e to the u du, the answer is just going to be e to the u. So I can answer that question as 1 over a e to the u plus c. And at this stage, you should be thinking, I don't want to use u in the final equation. I know what u equals. It equals ax plus b. So my final answer will be 1 over a e to the ax plus b plus c. And that's us using integration by substitution to get our final answer. And you're probably thinking, why can't I just do the exponential like I did earlier on? It's a lot easier. Just imagine if that was sine ax plus b. You wouldn't be able to use the formula quite as easily for that. Okay, so what I'd like you to do, just have a quick go yourself. All right, think about the inside function. If you're using chain rule, what would be your inside function? That should give you an idea of what to use for the substitution. Okay, once you've figured that out, have a go at these 4 integrals there. Okay, so pause, give yourself time to do them, and then we'll have a look through the answers. Okay, so this first one, hopefully you looked at this, do this one together, and you thought my u value is going to be 5x minus 2. So I've got 5x minus 2. I can then say, now that's 5x minus 2, I can work out what du over dx is. So I've got du over dx, and that's going to be equal 5. And a bit of rearranging, so I can take the dx over that side. That can be du equals 5 dx, but because I want dx on its own, because I'm substituting in there, I'm going to work it out to be 1/5 du equals dx. So I get that sort of answer just there. Okay, so now I know what dx equals. I know I can replace this bit for u. So I'm going to end up with 1 over u. Okay, so the integration of 1 over u du, because the dx is equal to 1/5 du, and the fifth I'm just going to move to the very front. So there we go. What does that become? Hopefully you remember the integral of 1 over u is ln u. But ln u, or u, is 5x minus 2. So your final answer, and I'll get the rubber out because that's messed this bit up. Oh, let's try that again. There we go. So your final answer will be 1/5, which came from there. 1/5 that came from there. The ln, because it was 1 over u, so that's where the ln came from. There's your u value, 5x minus 2, plus your c value. And don't forget, because ln only works for positive answers, you must have these modulus functions around it to say we only accept positive answers for this thing to work. Okay, ln only works for positive answers, hence you must include those modulus functions. Okay, right, have a go at this one yourself. If you need to pause, that's fine. Let's think what we did. So we've got u equals 4 minus 7x. So therefore, du over dx will equal minus 7. So therefore, a bit of rearranging would tell you that you're going to have 1 over minus 7 du equals dx. That would be the only difference. So this will be minus 7 here. The 3 can come out. So I'm expecting 3 over minus 7 at the front. Sine, as we know, differentiates to cos. So it must integrate to minus cos. But the minus from that and the minus from the minus 7 is going to make it back to positive. So it's positive now because of the minus from that and the minus from the cos. 3 is the same as there. The 7 came from when you rearranged from the 7. And then you've got cos of 4 minus 7x plus c. And you'll notice the same as the chain rule, your inside function reappears in your final answer. Your inside function reappears in that final answer because it's part of your substitution. Okay, try this one yourself. Again, pause if you want a quick go. Right, let's see how you did then. So in this one, I'm thinking that u equals 3x plus 5. So I've got that. Put plus sign in there. So 3x plus 5. So therefore, when I do a bit of rearranging, I'm going to get du over dx equals 3. So I get a 1/3 du equals dx. That's what I'm going to end up with. So with a bit of rearranging, I know what dx equals. That equals a third du. A third times 6 to me is going to equal 2. So I'm expecting to have a 2 at the front. U to the power 4. Now if I integrate something to the power 4, that's going to go increase the power by 1, divide by that new power. So I'm expecting u to the power 5 over 5. 3x to the power 5. Sorry, 3x plus 5 to the power 5 over 5. There's that first bit. The extra 5 goes underneath. Why is it 2? Because it's 6 and a third there. Okay, so that's where those two bits would have come from. Okay, so let's look at this last one. This last one's a bit weird because we've got like a mixture of an x squared there and an x cubed here. And this is more the sort of standard one you might get because it involves a bit more thinking. Now this is still my inside function. Okay, so let's do this one a bit more slowly. I'm going to let u equal x cubed minus 3. It might be wrong. That's fine. I'll figure it out in a minute. If it is wrong, I need to go back. I need to have another rethink about what I might do. Okay, but let's just go with it for a moment. So u equals x cubed minus 3. Now the issue comes when I try differentiating it. So du over dx equals, in this case, 3x squared. And that's a bit different to the others because in the other ones we end up with a nice number and it was all fine. And this one we seem to be messed up. But if I still rearrange it, because I still want to work out what the dx is equal to, okay, so I still want to work out what this dx is equal to. So I'm going to rearrange it and I'm going to get 1 over 3x squared. So that's fine. I can rearrange it to that. Du equals dx. So I know that that dx value just there is equal to 1 over 3x squared du. So if I replace that in, if I made that dx there 1 over x cubed, so 1 over 3x cubed du, what's going to happen is that 3x squared that I'm dividing by and this 3x squared here are going to cancel each other out. So it's actually worked out quite nice. That 3x squared there is cancelled with that 3x squared there. I'm still left with the du, which is great. And I'm still left with u squared. And u squared is going to go to u cubed over 3, which goes to x cubed minus 3 cubed over 3, which is where you get the final answer from just here. Okay, just get rid of that bit of writing. So we get 1/3 x cubed minus 3 cubed plus c. And of course you could do your chain rule and you could show that it gets back. If I did do a chain rule very quickly in my head, x cubed minus 3 goes to 3x squared. That's where that front bit comes from, 3x squared. U to the power 3 goes to, bring the 3 to the front, cancel that third, makes it a squared. There we go. So you can see how chain rule will get you back to this bit just here. Okay, right. So we're going to look at some standard integrals. Now if you want to just pause it, have a quick go. This first one we already know, we've just done. Okay, so that one we've looked at. Next one I want to look at is that. Okay, so think about just doing it yourself. Okay, so pause it, have a quick go yourself. Ax plus b being your substitution, see what you get, and lo and behold, we get 1 over a ln ax plus b. Okay, because you think of it as a bit of 1 over u, it's the same sort of idea. What about sine ax plus b? Okay, so if you want to pause it again, what happens to that then? Well, we end up with 1 over a cos ax plus b, and because it's sine, it goes to minus cos ax plus b plus c. Right, cos, same idea, but this time it's sine. Okay, but the bit there goes to just a, so when you rearrange it for du, you can see where the 1 over a comes from. And finally, if I had ax plus b to the power n, what does that go to? No surprises, 1 over a, okay, still 1 over a, and the other part, because it looks messy, doesn't it? It looks like it's different to the others, but it's not. Look what you're doing. You're increasing the power by 1, and you're dividing by that new power. So the 1 over a is the same as all the others, or the previous ones, And this n plus 1 is just part of the rule for integrating something to the power n. Okay, so there's nothing different about that at all. It's always times by 1 over a. So if you've got some straightforward linear function inside your substitution, it's very easy to get the final integration. And that's what we call integrate. We call that chain rule in reverse. Because we've noticed that as a differentiation on the front, it's very easy to work it through. Okay, so you can either learn those off by heart or you can do it as part of substitution. Right, it seems like a lot of exercises there. There is a lot of exercises there, but that's because there's a few that are just integrate sines, integrate cos, integrate e's, and integrate some of the other functions. That's a bit of a mixture. Okay, so pick and choose which ones are appropriate. If you've got sort of lots of the same questions, don't feel you have to do them all. Just do what you need to do to fully understand it. My advice is always to go for some of the harder questions in there as well. Okay. All right, so let's have a quick look at using the chain rule. So we did the chain rule, we do this, don't we? We integrate, we did the chain rule, so we differentiate the inside function and an outside function. And how do we differentiate it? We differentiate the inside function first, so we call that f dash x. And then we differentiate the outside function second, but we leave that inside function alone. So very mathsy that, but that's basically what you do. Inside function differentiated, outside function differentiated, times those two together. Okay. Now the reason why we talk about that is we can talk about what we call the chain rule in reverse. If I'm differentiating this function and get this, then what I can notice is if I just integrate both sides, in other words, if I integrate this, I should get back to that. And what we're getting at is if we notice that we've got a function and the inside function just there and the differentiation on the front, then the answer is just going to be the initial function with the same inside part. Okay, right, we'll have a look at one and I'll explain it. So if the integral is both the inside function and the outside, then we can use chain rule in reverse. That's the key thing that you're looking for, that you have an inside function and a function on the front of it, which is the integration of it. Then we can use integration, the chain rule in reverse. Okay, so yes, the answer will be just the integral of the outside part. So we look at an example because that'll make it a bit easier. Right, so look at this function just here, and we notice that apart from the 6, so I'll give you a chance just to get it down. Pause if you need to. So in this function, I've noticed that I've got an inside function just there, if I was using the chain rule, and I've got a function on the front just there. And I noticed that if I integrate that, I would get that. The 6 is messing me up. So what we can do is we can sort of pull the 6 out to start with. Okay, so we can pull that 6 out, and that makes life a little bit easier. The problem is, why have I left the 2 in there? Now, the reason why I leave the 2 in there is because the differentiation of e to the 2x, I know, goes to 2e to the 2x. So what I've done is a bit of cheating really. I've pulled the 3 out so that then I've definitely got the differentiation of e to the 2x on the front. Now if that is the case, which it is, if I differentiate e to the 2x I get 2e to the 2x, then all I need to do to get the answer is just the differentiation or the integration of cos. So I notice those two are the same, that's why I've done it. So what can I do? I can use chain rule in reverse, and I know that that is going to go to 3 sine e to the 2x, because all I've done is integrated the cos part to get to sine, plus c. Now some people like integration, chain rule in reverse. Some people prefer chain rule in reverse. Some people don't like it because you have to notice these little things like that. What I recommend for anybody who doesn't like it or doesn't notice it quickly is just go for integration by substitution. In fact, chain rule in reverse is just integration by substitution. It's just a very easy version of it because you've got the differentiation on the front. Okay, so let's have a look at this. Exactly the same question, but for most of you, you probably just prefer to do this and not worry about chain rule in reverse at all. So if I'm going to use integration by substitution, I still look for that same pattern. I've got a function of a function. So the inside function is e to the 2x. So I'm going to let u equal e to the 2x. I then differentiate it like I did before. Du over dx gets me 2e to the 2x. I can rearrange this because I want to work out what dx is. So a little bit of rearranging, du equals 2e to 2x dx. And then from there, I can work out what dx is. So there we go. Dx is 1 over 2e to 2x du. The same skills that you were practicing a minute ago. Okay, so why does that help me? Well, now I can replace my dx into there, and I get this. So I'm replacing the the e to the 2x for u in there, and I'm going to replace the dx at the end. I'm going to leave this front function alone. I'm not going to touch it. Okay, so I know that that goes to this. Notice I'm not bothering touching the front bit. Don't change that for u or anything silly like that. Just leave it alone. And if later on you need to do something with it, fine. But at the moment, I'm just going to leave it because I'm hoping that this is going to help me cancel it out. And as you can see, it does. The 6e to the 2x divided by the 2e to the 2x cancel out quite nicely. 6 divided by 2 is 3. E to the 2x cancels out e to the 2x, leaving me just 3 cos u to be integrated. What's the integration of 3 cos u? Well, cos differentiates to minus sign, so it must integrate to positive sign. So therefore we get 3 sine u plus c. U is e to 2x, so therefore that's just going to go to that. Okay, so it takes a bit longer to do integration by substitution as opposed to chain rule in reverse, but you're guaranteed to get the right answer and you don't have to look for spotting that pattern between those two or pulling out the 3 and things like that. Okay, but it's up to you. If you can spot it, great, but if you can't, don't worry, just stick with integration by substitution. Okay, so you've seen the two skills, integration by substitution and chain rule in reverse, which of course is just integration by substitution. So when it comes to these exercises, feel free to use whichever skill comes best to you. So if you feel more comfortable just doing chain rule in reverse, by all means stick with that. If you want to do integration by substitution, that's fine as well. You don't need to know both sets of skills and you get the same amount of marks for using either of them in that exam. Okay, so make sure you do practice all of the skills on those two exercises. Okay, so I'll give you a moment to have a go at this one yourself. So pause if necessary. Remember it says differentiate, it does not say integrate. Okay, so let's see how far you got then. So if you're differentiating it, you should be thinking chain rule. You should be thinking, if I differentiate this, I've got an inside function, I've got an outside function. And if I differentiate it, I'm going to get the inside function differentiated goes to 3x squared plus 4x. The outside function is 1 over. So that's 1 over the inside function, which is where you get this part from. But what you can notice is that the denominator differentiates to the numerator. And this is not unique to this one example. This is always true for the Lund function. That when you differentiate the Lund function, you always get the denominator differentiated to be the numerator. Now this fact is quite important. It's important when it comes to the other way around. If we differentiate and it always goes to this, if we can spot this pattern, we should be able to integrate it and get back to the Lund function. And that's where this rule comes from. If I differentiate the Lund function, I get a function and its differentiation on the top. Doesn't matter whether that inside function is a polynomial or sine and cos, it doesn't make any difference. It's always true. So that would lead to this general rule, if I use chain rule in reverse, that if I integrated this function just here, my answer would be ln of the function. Notice the modulus sign's coming back in because it has to be positive. Okay, just generally put those in every time you write the word the ln function, just put those mods in. Okay, so we know that fact from previous lessons and now we're just adapting it to this. So what that means is if you spot that you've got a quotient and the numerator is the gradient function of the denominator, you can just use this rule. Okay, again, pause if you need some more time. That formula is given to you in the formula book. but your job is to spot when you can use it. Okay, so let's have a quick look at an example. So just while you grab your notebooks and get the question down, I want to show that the integration of sine x over cos x equals ln of sec x plus c. Notice the mod signs because it's ln. And you might have had this written down as tan x, the integration of tan x. But I'm just being kind to you. I'm writing it as a quotient because I want to look at using that previous rule of the bottom differentiates to the top. The denominator differentiates to be the numerator. Okay, so pause it if you need to, if you want to go yourself. Okay, so let's have a quick look. So the first thing I've noticed is that I want to use this, but there's a bit of an issue. The denominator doesn't quite differentiate to the numerator, but you can do a little bit of cheating. What you can do is you can just change this slightly. You can say to yourself, look, I really want a minus sign there, because if I had a minus sign there, then I would notice that the differentiation of cos goes to minus sine, and this is perfect. But I can't just put a minus sign on the front there without having a second minus sign on the front. So it's a bit of cheating. Minus and minus makes a plus. It's basically you doing minus 1 on the front times by minus sine x. So you can think of it like that if you want to. Minus 1 times minus sine x is positive sine x. So it's the same thing, but I've just cheated. I've cheated so I could use this rule. That's why I could write integration of sine x over cos x, because I've put the minus there and the minus 1 on the front. Okay, so that's okay. It's the same thing. The answer comes out to be minus 1 lot of ln mod cos x. And that's the same sort of thing if you had something like, give me an example, if there was a 2 on the front. Okay, so you could say, well, if there was a 2 on the front, it would mess me up there, wouldn't it? Mess me up because if I've got a 2 on the front, I can't do anything with it. But you can. You can take that 2 and you can just pull it out. So therefore, it would be fine. Okay. And the opposite's true if you need a 2 on the front. So if you had something like an integration with x squared on the bottom and you had just an x on the top. Okay, now obviously that's a very simplistic idea because you'll just write it as 1 over x, but let's just pretend for a minute. So on the top here, if I wanted this to be the same at the bottom, I need a 2. So what I could do is I could cheat, I could put a 2 on, but I could take a half outside because the half and the 2 just makes 1. So you're allowed to manipulate it, you're allowed to sort of cheat and get you whatever number you need so that you can apply this rule. Okay? Right, and you will have to with some questions. Right, so let's go back to this one. So we've just, let's get the correct pointer. There we go. So I've just integrated sine over cos. I've cheated by putting a minus sign in, and that's where I've come down to this answer. I'm allowed to do that now because the denominator differentiates to the numerator. Right, but that's not the same as this, is it? This is a cos, this is a sec. Right, so I can use my laws of logarithms though, because I know that if I put a minus on the front, that's like minus 1, all right, like it was here. So I can think of that as minus 1 ln cos x. So what that means is I can actually take that power up to there. So really, it's going to be ln of cos x to the minus 1. Okay, cos x to the minus 1, isn't that 1 over cos x? And isn't 1 over cos x exactly the same as sec x as required? Sine over cos, of course, is tan x. And that's where you get that formula from in your formula book. Okay, so that formula just there is what you get in your formula book. So this exercise here just allows you to practice that skill when you've got a function on the denominator and its differential on the numerator. Okay, let's try this one. So integration by substitution, and you might think, right, I'm going to use chain rule in reverse. Now, if you think about using chain rule in reverse, you'll notice that the inside function in this case does not differentiate to the outside function. Right? The inside function goes to just 3. It's 12x on the front. Right? If this was an x squared, that'd be great because then that would be something to work with. But we can't use chain rule in reverse. So you people out there that like chain rule in reverse, great, you're stuck with this one. Everyone's going to have to use integration by substitution. Okay, so let's see why. Hopefully, you figured out that you're going to be using 3x plus 2. That should be a starting point. As I said, sometimes it might not work. If it doesn't, you have to have a rethink. But in this case, that should be a good starting position, your inside function. Let u equal 3x plus 2. So what I end up with is du over dx equals 3. Bit of rearranging. Du equals 3 dx, so therefore dx equals a third du. Fine. When I replace that in, unfortunately, I've noticed that this x value here I'm sort of stuck with. So when I substitute them both in, looks good. Yep, great. Normally, this thing cancels out, but I've got a bit of an issue on this because before here I had u's and x's. Now I've still got an x value in and nothing's cancelled it out. It's not been a situation where this denominator cancelled with this like it was in the previous example. I'm stuck with this x value. Okay, but integration by substitution doesn't just substitute in for that part and that part. You might have to use it to substitute in yet again. And that's what you're going to do in this case. I don't know what x is. Okay, I don't know what x is. So I can't differentiate it to u or integrate it in terms of u. But what I can do with x is I can rearrange it using this equation just here. So if I look at this equation just here and rearrange it to make it in terms of u, then what I can do is I can substitute that in as well, and hopefully that might give me something that I can integrate. It seems like you're going to get in even more of a mess. So let's just try. So yes, I come down to that fact, so the 12 and the 3 can cancel with 4, but this x is what I'm stuck with. So what I'm going to do is I'm going to rearrange this equation and get u value from there. So I rearrange it and I get a third u minus 2. I can substitute that in. Okay, so 4x u to the 5 du can go to this. 4 lots of 1 over 3 u minus 2 u to the 5. And it looks like I've gone from something like that to something just as hideous down here. But there is a major difference. Okay, so just neaten it up slightly. Okay, so maybe pulling the 4/3 out. There we go. And look at the difference. This one here has got u to the 5, right, the single variable there to the power 5, and the u minus 2 as a linear function inside a bracket without any power, or power 1. Whereas up here, what we started with is the 3x plus 2 to the power 5. Now, if I imagine expanding this, I'd have to use my binomial expansion skills up to power 5. If I imagine expanding this, that's a lot easier because it's just u to the 5 times u and 2 times u to the 5. So in fact, I could actually expand this really easily. That would have been a nightmare expanding. This is a lot easier. Right, now once I've expanded it, this is actually boiled down to something very easy. U to the 6 goes to u to the 7 over 7. 2u to the 5 goes to 2u to the 6 over 6. And there we go. What can I do at the end? Take my u value, 3x plus 2, and substitute it back in to both of those two places. And there we go. There's my final answer. Okay, so pause if you need to take notes down. Because we just need to figure out the last bit. So unfortunately, this is the part that people sometimes struggle with. Okay, you've done all the hard work, you've done the substitutions, you've done the integral, you've got the majority of the marks, and then some people just lose out on these last marks because they struggle with the simplifying part. Right, so what we're going to do is we're just going to look at these two parts just here, and we're going to factorise them. So if I look at these two and think, what can I pull out of this factor? I notice that 3x plus 2 is common in both. And in fact, more than one lot of 3x plus 2 is common in both. In fact, there is 6 lots common in both. I can pull out 6 lots from there and 6 lots from there. From a fraction point of view, I'm thinking of a common factor of both a 7th and a 3rd. So the only answer I'd think of there is 21, because I could just times it together. What I'll do is just neaten it up, take out the factor of 3x to the power 6, all right? And again, just check you're happy with that. 3x plus 2 to the power 6 times by 3x plus 2 is 3x plus 2 to the power 7. 3x plus 2 to the power 6 times 1 is 3x plus 2 to the power 6. So that's where that part comes from. Okay. I can put these together, get it over 21. So 3 lots of that minus 7 lots of that, all over 21. And then once I'm in that stage, I can then just simplify this bracket. And there we go. I might be able to sometimes cancel these down a bit. I can't in this case. 63 and 4 are as good as they're going to get. So therefore I've got my final answer. Okay. Right, that's why sometimes when you look at your answer in the back of the book, you might have got to this stage, you look at the answer in the back of the book and it's like this, and you think you're wrong. You're not, you just need to factorise it as well to finish it off. Okay, so I just want to mention a little bit about definite integrals. A definite integral is one where you have a pair of limits as opposed to just finding a general integral that you've just been doing. So if you've got a pair of limits and you need to solve a definite integral, as you know, you would solve the integral and then you would substitute in the upper limit and you would minus the lower limit. Now this is exactly the same when you do an integration by substitution, except you need to be wary of something. In this integral just here, the 1 and the 3 represent x values because everything is in terms of x values. Whereas when you actually went through and started to solve the integral and you had to use a substitution, for example, u equals 3x plus 2, notice I've missed the limits out on purpose because it's very easy just to make the mistake of putting in 1 and 3 again. Now 1 and 3 represent the x values, the x limits. So it'd be wrong mathematically to put 1 and 3 as the limits on this equation because this equation is in terms of u. So what you can do though is you can replace the limits 1 and 3 for u values. So instead of x equals 1 and x equals 3, you can replace them for u values. So for example, when x equaled 1, you can replace that for u equals 5 because 3 times 1 plus 2 is 5. And when x equals 3, the upper limit, 3 times 3 is 9 plus an extra 2 is 11. So you can rewrite an integral like this, but make sure that when you put the limits in, you use the appropriate limits. Those are for the x values. Those two would be for the u values. Now what you can do is then you can solve this integral and you could substitute u equals 5 and u equals 11 straight in. You don't need to convert it back to x. Just be very wary though, is if you do the integral and then you convert it back to an x equation, then you need to go back to your original limits. Okay, so what I'd like you to do is just to practice a few of those new integration skills, integration by substitution, where you have to replace not just the dx part, but you're also going to have to substitute in an extra part of it. It is worth making sure that you practice all the exercises in 9.1. 9.2 look a little bit about definite integrals, and again it's worth practicing all those just to make sure you've got a handle on replacing and changing limits. Okay, look at this one. Show that the integration between 7 and 8 of that can be written in the form ln k. If you dive for your calculators and try putting your calculators, you might find that your calculators write it as a decimal and don't write it in exact form. That's why the examiner asks for it in exact form. So it forces you to use your skills. Okay, so let's have a quick look at this. So the first thing I'm thinking is, does the denominator differentiate to the numerator? So if I do it, and don't just go no because that's 7, because what you might find is that you can multiply by a common number to get the correct answer. So if I had, in this case, I differentiate the bottom, I'm going to get 2x minus 2. There's no way that that's going to be a multiple of 2x minus 2, so I can't use the ln rule from the previous exercise, the previous example. So how else can I do it? I could try using that as a u value, okay, and then I'd get 2x minus 2 as part of my substitution. Again, that's not really going to help, and I can't really rearrange to me an x value, so there's got to be another option, and the answer is written in the title. We're going to be looking at using partial fractions. So what I'd like you to do is just write 7x plus 8 over x plus 4x minus 6. So there you go, I've helped you out slightly in partial fractions. So pause there, use your partial fraction skills, make sure you're happy and you can write that in partial fractions. Okay, So hopefully you wrote it as a over x plus 4, b over x minus 6, and you managed to get 2 and 5 as your a and your b values, and there you go, you've got it in partial fractions. Why would you want to do that? Well, now that you've done that, you should notice that the bottom differentiates to the top if that 2 was taken outside that integral. Same here, bottom differentiates top. So you've got two functions similar to what we had previously where we can use the Ln function. And in fact, that's where we're going to get the final answer from. 2 ln x plus 4, should we have mod signs around it, 5 ln x minus 6 plus c. Why is there no plus c? Because we've got a definite integral. So we're looking at putting in these values at the end. That's part of the reason why there's no mod functions in there as well, because we are putting in 7 and 8. So I can do that. I can put in the 7 and 8, and most of these skills you should know how to do yourself. So there we go. I can put the number 8 into it first. I can put the number 7 into it. I can simplify these down as much as possible. And so I can take the 2's up to the powers. I can take the 5 up to the power 2 there. Notice ln 1 is 0, so that's just going to be 0. So we'll get ln to the 12 squared plus ln to the 2 to the 5 minus ln to the 11 squared. And because I can use my laws of logarithms again, adding is the same as timesing them. That's where that bit comes from. Minus is the same as dividing. That's where you get 121 from. And there you go. You're in that final form of ln k. And of course, you could check that answer compared to the decimal your calculator got, and they should be the same. It's a nice way to know if you're right. Okay, so lots of different examples there, lots of different techniques that you might have to think about using when it comes to integration by substitution. Right, have a quick go at this exercise. It involves using partial fractions with integration. Okay, so what I'd like you to do, grab your notebooks and just jot the product rule down, or that first bit of the product rule. You might want to wait till I put the rest of it down formally. Okay, so if I asked you what the product rule was, hopefully you would say you could differentiate the first function, leave the second function alone, and then you could leave the first function alone and differentiate the second function. Just notice if you're thinking, where's the y gone? All right, this is shorthand notation. It's basically saying to you, you're differentiating this function in terms of x. You don't need to put the y in. I'll show you the example where the y comes from. So if you had y equals 2x plus 3, and your teacher says to you, can you work out dy over dx? You would then say, yep, I can differentiate the y equation in terms of x, and the answer is just 2. Nothing wrong with that, perfectly correct, but you can be lazy. You can combine those two things together. You can say, I would like you to differentiate the y value, but the y value is 2x plus 3. So you could write the 2x plus 3 just there, and the answer is 2. So what you've done is you combined those two things together and just wrote it in a single equation. Can you differentiate 2x plus 3 in terms of x? Yes, the answer is 2. That's why you write dy over dx. All right, it's the exact same thing. Right, so that's what I'm asking you here. Can I differentiate uv in terms of x? And you say, yes, I can, because I can know what the product rule is. So therefore, the answer is going to be u left alone, differentiate the v, plus differentiate the v, leave the u alone. Okay, and that's where you got those two parts from. Now, the reason why I'm repeating the product rule is because what I'd like to do now is just integrate it all. Okay, I integrate both sides. I integrate that side, and I get that in terms of x, and I integrate this, and I get this in terms of x. Right, why would I do that? Well, I know that if I integrate and differentiate, because these two are the opposites to each other, they will cancel each other out. If I differentiate that function and then integrate that function, I would get back to where I started. That's not the case on this side, because you're integrating some function and you're also integrating something that's been differentiated. Now, if that u wasn't there, that would be fine. It would just be v, but the u's messing it up. This side's perfect. uv differentiated and integrated leaves uv. If it's just a v, that'd be fine, but the u's messing it up. So what can I do? On this side, which is what I just said. I can differentiate it and then I've integrated it straight away. So what I end up with is just UV. But this side, I can't do anything with, but what I can do is I can separate it out. I can expand it. All right. Right, so what I'm going to do now is I'm just going to rearrange. And if I rearrange it, I get a formula for what we call integration by parts. And that is the formula for integration by parts. And luckily for you, you don't need to learn it. You might be asked to show it from the product rule, which is why it's in your notebooks. An examiner might have expect you to either show that, or it might give you part of the proof and you have to just put some parts in. It doesn't really matter, but you do need to know how to do it. But you do get given this in your formula book. Okay, so you don't need to learn it off by heart, you just need to know how to use it. Okay, that's what we're going to look at now. Look at an equation, so pause if you need to. Okay, so in your notebooks, looks nice and easy, find the integration of that function. Okay, so the first thing I've noticed is that I could try substitution. If I tried substitution, I put 4x as my u value. Okay, it's a quarter, but that doesn't cancel out with that. But then I can't put the x value back in because I can't really rearrange it that easily. Okay, if I let u equal 4x, the x value doesn't cancel out. So it doesn't matter what I try, it doesn't work out that nicely. Okay, I'd end up with a similar equation if I did substitution. So I'm going to use a different technique. I'm going to use integration by parts. And I'm going to write this bit down. Now, just the way we write it sort of shows what you need to do. We're integrating two functions times together. So one function is the u function, and one function is the v function differentiated. Okay, so one function there could be the 3x, that could be my u value, and the other function could be my cos 4x, and that's the one that's been differentiated. So if I differentiated it, I've got cos 4x, I will have to do some integration to find out what v is. Okay, so that's what I'm going to go with. I'm going to let u equal the 3x part. Okay, and I'm going to get the dv over dx to be the cos 4x part. So I'll write both of those down. I didn't write them down because they're in that order. Okay, so that's what this says. Just be aware that you could do it either way round you like. Okay, so my u value could have been my cos 4x, and my v value, my dv over dx, could be the 3x. But there's a reason why. Okay, and we'll come back to that in a second. Okay, right, so what do I need to do? Well, to get the answer, I need u. Great, I've got that, it's 3x, but I need v. That means I'm going to have to integrate cos 4x to get v. And that's okay. I can integrate cos 4x because I know it goes to a quarter sine 4x. Okay, what else do I need? I need du over dx. Well, that's okay as well because I can differentiate u in terms of x to get du over dx equals 3. And this is what is important to do it that way around. That differentiates nicely to get to 3. And that integrates nicely to get a quarter sine 4x. If it's the other way around, I would have had to integrate 3x and I would have got 3x squared over 2. Okay, now it's getting more messy. It's going from 3x to 3x squared. Whereas if I differentiate it, it goes from 3x down to the number 3. So it's a lot neater. Okay, so let's have a go. So I differentiate u equals 3x to get du over dx equals 3. So I've got u and I've got du over dx. Tick, tick. I've also got dv over dx equals cos 4x. So v equals a quarter sine 4x. Tick, tick. So what I can do now is just basically fill in this formula, stick in the u value, that's the 3x, stick in the v value, that's a quarter sine 4x, stick in the du over dx, that's 3, and stick in the v value, that's a quarter sine 4x. Okay, so I can rewrite it, stick in my uv, there's those two parts, minus, stick in my du over dx, which was 3, and stick in my v again, which is a quarter sine 4x. Notice that with integration by parts, you're going to have to integrate again. Okay, so I've integrated and used the formula once, but then I'm going to have to integrate the formula again, just here. That's fine, we can do that, because now, if you look, 3 over 4 can be taken out. How do I integrate sine 4x? I go to minus a quarter cos 4x. The minus goes to a plus, because it goes from sine to minus, minus is a plus. The other quarter goes with this, and that makes where the 16 comes from. So just check you're happy where that 3 over 16 cos 4x comes from, plus c. And there's your final answer using integration by parts. Okay, so pause if you haven't got it all down. Let's have a look at another one. So I'm integrating by parts, just to make sure we've got another, we're happy with another answer. So what do I differentiate? What do I integrate? Now your go-to place should be 12x being the one that you differentiate, because it's realistically that 12x is going to be the one that goes down to just 12 when I differentiate. That makes life a lot easier. So my answer is going to be, let u equal 12x and let dv over dx equals 3x plus 2 to the power 5. I do have to integrate this, okay, which is not easy, but I can manage. So I differentiate the 12x, which goes to 12. That's fine. That ticks off that one just there. I do have to integrate 3x plus 2 to the power 5. That's one of those standard rules, but feel free to do integration by substitution if you need to. It's going to be 1 over 3, bring the 5 to the increase the power by 1, divide by that as well, which is that saying here, just your standard rule that you might have remembered, which is where that bit comes from, or integration by substitution. And once you've got both of those bits, we can just fill in the gaps. We can fill in the u value, we can fill in the v value, we can do the du over dx is 12, we can fill in the other v value, but I'm going to have to integrate this bit again. But just make life easy for yourself, pull that 12 over 18 out, and then deal with the 3x plus 2 to the power 6 again. That's integrate the differentiate the middle, which gets you 3, increase the power by 1, which gets you 7, divide by 7, and the 7 and 3 make 21. So you are going to get quite a big fraction on there, but it all cancels out nicely to give you 2/3 at the very end. Okay. Right, so once you're happy with that, don't forget the plus c. Then we need to just do that second bit of integration. Okay, so there's the 2/3. So that's where the 21 comes from that part just there. And that's where you finally put in the plus c. We can neaten this part up, and same as previous, you might get to that point and say, right, I'm done. You check your answers in the back of the book and they give you some different answer. And the reason why they might give you a different answer is because they've done some factorizing. Okay, they've looked at these two answers just here and they said, right, we can actually pull some parts out to be factorized. For example, the 2 can come out, the 3 can come out because 63 is 21, so that's fine. We can also pull out a 3x plus 2 to the power 6 and a 3x plus 2 to the power 6 from both of those parts. The x we're stuck with because there's no x on this bit. So we can simplify it down. I'm just writing 2/3 as 42 over 63. And the reason why I'm putting that up is just a little bit of a reminder that if you put in a common factor of 63, that helps you with your factorising. If I can put these two as a common factor, then you can see that you can pull out a 63rd as an option for both of them. There's 42 of them there. Okay, so if I pull out 2 63rds, then that's where the 21 comes from. 2 times 21 is 42. 42 over 63 is back to 2/3. What else is left there? Well, they've got an x, so I've basically got 21x for that. With this one, I can pull out the 2 over 63. That makes that fraction gone completely. I've pulled out 3x plus 2 to the power 6. I'm still left with one of those, hence why there's the one I'm left with just there. Okay, can you double check? That times that got this first bit, and that times that gets me the second bit, plus c at the end. This will neaten up, 21x minus 3x plus your 2 at the end, and there we go. Often the actual factorising is more difficult than the integrating. Okay, people struggle more with that bit than they do with trying to get this part. Okay, but that's more likely to be the answer in the back of the book, so well done if you manage to get down to that. Last bit of simplifying, just pulling out a 2 from there, which is where the 4 went to that bit. Okay, so one last bit. If I'm integrating ln x, So integrating ln x, which is not 1 over x. Remember, be careful. That's if you're integrating 1 over x goes to ln x. If you differentiate ln x, you get to 1 over x. But what happens if you want to integrate ln x? Right, so we haven't done that yet. Now what we're going to do is do something a bit weird. I'm going to write ln x as 1 times ln x. So instead of writing just ln x, I'm going to write it as 1 times ln x, which seems a bit weird because it is the same thing, of course. 1 times ln x is just ln x. But the reason why I'm writing it like that is what I can do now is I can use integration by parts. So it's a bit of a special case. It's a special case for ln x. I'm going to use integration by parts. And when I use integration by parts, I don't know how to integrate ln x. So there's no point in putting that bit down as your du over dx bit, because I'm going to have to integrate it. So that bit I know how to differentiate. So that's going to be the part that I definitely leave alone. I'll write that as my u value. So my u value has to be ln x. My dv over dx is going to be 1. Okay? There's no point in having it the other way around because you're trying to show you're integrating ln x. There's absolutely no point to it at all. So it has to be that way around. Okay, so what does that mean then? Well, I've got du over dx is 1 over x. That's the bit I do know. Dv over dx equals 1. That goes to v equals x, which actually makes things more complicated. But let's see what happens. And you could try it yourself if you want to. I can stick the u in there. I can stick the v in there. I can stick the du over dx in there, which is 1 over x. And I can stick the v in there, which is x. So that's actually going to work out quite nicely. So I'm definitely going to get x ln x minus 1 over x times x dx. Now 1 over x times x is just going to get me just 1. And if I integrate 1 in terms of x, I get the same as what I've got up here, which is just x. So x ln x minus x plus c. The integration of ln x is going to be x ln x minus x plus c. And what I'd like to do is just pause there, have a go at differentiating that and just verify, is it right? If I differentiate this function, x ln x minus x plus c, do I get back to ln x? Okay, so just pause there. Okay, so let's see if you manage to differentiate it. Okay, so if I differentiate x ln x, I would have to use the product rule. So I leave the x alone, I differentiate ln x, so I get x 1 over x plus, other way around, so I differentiate that, which goes to 1. I leave ln x alone, so that's 1 ln x, or just ln x. Okay, then I carry on. I differentiate minus x, which goes to minus 1. And I differentiate plus c, which cancels out because it's just a constant. So I end up with x over x, which is just 1, plus ln x minus 1. And lo and behold, that one there will cancel with that one, leaving just ln x, which of course is what you wanted. Okay, so it works out beautifully. Some people just remember that if you integrate ln x, you get x ln x minus x. Some people learn that off by heart, but you do need to know how to prove it. And it's not easy to remember because you have to do this sort of weird little change there and writing it as 1 times ln x. Okay, so make sure you've got that on your notebook. Pause if you need to. Plenty of exercises to do with integration by parts. You can see why there's so many exercises to do on integration because it's so important when it comes to your exam at the end. It's worth making sure that you're absolutely solid on integration by parts and integration by substitution because there's a very good chance that both of them will be in your final exam at the end of the year. Okay, so just grab your notebooks and get that really quick question down. Find the integration of sine squared x dx. And then pause and see if you can have a go at working out what the answer is. Okay, so some of you might have tried to do integration by substitution because you might have thought, I know, I can have maybe sine x substituted in as u, and therefore I've only got u squared. But the issue with that is you end up with an extra cos floating around that you can't do much with. Some of you might have thought, I'm going to write it as sine x, and therefore can have it go integration by parts. And so you could get quite complicated with integration by parts. And although you can get somewhere with sine squared, it's not easy. It's not straightforward. So what we're getting at with this question is that you don't always have to make things complicated. Sine squared x is something that you've seen before. And you've seen it before with a trig identity. So I'm not talking about the most basic trig identity that you've seen, sine squared plus cos squared equals 1. I'm talking about another trig identity that you've seen with sine squared in. And the answer is where you've seen it before is actually one of the double angle formulas. So the double angle formula that you've seen sine squared in is this one just here. When you expanded cos 2x using your compound angle formulas, it became 1 minus 2 sine squared x. There's actually 3 different versions of this one. Okay, some with cos squared in, some with sine squared, and one that's got both sine squared and cos squared in. So the one we're interested in is this one just here. Cos 2x equals 1 minus 2 sine squared x. Why are we interested in that? Well, if I use that and rearrange it to get sine squared, so in other words, I divide everything by 2 and I take the 1 over the other side, or the half in that case, then what I end up with is this equation just here. So sine squared rearranged would get me 1 minus cos 2x, and if I divide it by 2, I get a half minus a half cos 2x. Now what I'm going to do is I'm going to replace my integral. So I've got the integration of sine squared. So instead of the integral of sine squared, I'm going to write that as a half minus a half cos 2x. Once I've got that equation just there, I can now integrate it easily. The integration of a half dx is just going to go to half x, and the integration of cos 2x is fine to do. I can integrate cos 2x because it was going to go to a half sine 2x. It's the squared that messed you up, it's not the 2x. All right, we've differentiated and integrated cos nx functions before. So there we go, that's the answer I'm going to look for. So I've got x over 2, which is that part just here. I've got the cos 2x goes to sine 2x over 4, which you can see just there, plus your constant of integration. Right, so now we've had a look at some of those, or one of those. What I'd like you to do is have a go at practicing just using some different trig identities in these exercises here on 6.1 and 6.2. So they all involve using different trig identities, so have a quick go at those.